example, in a phishing attack, and you try to follow that email, it won't be that link in that email would not be valid after 5 days or so, because botnets are often shut down quite quickly. But if a botnet was used to launch denial of service attack, they can actually use legitimate IP addresses and still do denial of service attacks. So spoofing prevention will not prevent that kind of denial of service attack. But in that case, if they're using their legitimate IP addresses, you can at least shut them down the way you shut down spammers today. So in general, the current approaches that are used to prevent IP spoofing, or that have been proposed to do IP spoofing, fall in sort of 3 broad categories. The first is traceback. In this approach, either basically the routers help in detecting the actual path a packet took. For example, in the picture that I showed earlier, if the path of the packet was not as if the packet was coming from what it was claiming to be, if the packet was coming from place X, but it was actually coming from Y, it would most likely take a different path. In the picture I showed, it would actually take the same router path, right? If you can detect the exact path of that a packet took, you can detect who the spoofer is with some probability, right? Does that make sense? A packet containing a valid source address has to traverse a certain path, because that's how the routing protocol is set up. If the packet claims to be coming from somewhere else, it would take a quite different path in order to reach the destination. However, if the end host had some information that would help it detect the exact path that a packet took, then it can still detect, it can still say who sent the spoofed packet. Is that obvious? Does that make sense? Right? However, this does not help you stop anything. This only helps you find out where the packet actually came from, and maybe you can use it in your law enforcement or otherwise. So traceback approaches, there has been a lot of work in this area. In fact, in general, in IP spoofing prevention, this is the area that has received the most attention, which is that you want to trace the path the packets took rather than trusting its source address. And then you can use this information for apprehending the attacker. The other approach is mitigation, where let's say the source network and the destination network ahead of time exchange a key of some sort. It could be a simple text key, which means that every time the source network communicates with the destination, it is going to use that particular byte pattern, for example, bit pattern in its packets. If that bit pattern isn't known to other people, then no one could spoof that source to this destination. No one could do that, right? No? If I tell you whenever I'll talk to you, I will always end my sentence with I like you, right? Which means that if no one else knows our code word and they're not hearing us, then they don't know what my code word is. So if they try to talk to you as me, they would most likely not have I like you at the end of it. And you can detect it. However, this is happening at the source and destination networks, which means that the routers in between are, one, not concerned or not bothered with this whole approach, which is good, but at the same time, you're not preventing the routers from delivering bad packets. So the spoof packets will start from the source network, they'll traverse all the way to the destination, and they get dropped because the destination realizes that if I actually was hearing from this source, then the packets would contain some information that they don't contain. So you can prevent spoofing that way. You can prevent the destination network from receiving spoofed packets if it ahead of time exchanges the byte pattern or the bit pattern that packets from that source network will always contain, right? The third approach is prevention. What if we don't let the spoofed packets from getting into the network at all? And this is essentially the approach we are trying to pursue too. There are several works in this area, but the prominent ones is where you do ingress filtering. So let's look at an example of ingress filtering, because that is what we build on in our approach. So here's the same network. And again, this host on this red host is trying to send traffic as if it came from 5.6.7.8. So here's the sneaky packet, and the router has information about which interface the packet could come from. So it knows that in this case it's much. It may actually have to rely on hardware addresses because they are on the same interface. However, in general, routers in the network know like what IP addresses are assigned to other, what hosts are sending packets, and they know if the host is not sending the correct source address in its packet, right?
What about mobile IP? Like if you have mobile IP, this will not work, right?
If you have mobile IP, then where are you at this point? You are somewhere else, and your home agent is sending the packet,
Yes.
right? So if you have mobile IP, then okay, no, that's not true that it won't work. See, in mobile IP, even though you have gone ahead and acquired a completely new IP address in some other part of the network, your packet always first gets delivered to your home network, right? That's how it gets tunneled to the destination network, which means that, okay, actually let me backtrack for a second. This is happening at the source. So the sender of the mobile IP packet, it's actually completely independent of whether you're using mobile IP or static IP. It doesn't matter. The sender of the packet is responsible for guaranteeing that the IP address is not, that the source IP address contained in the packet is not spoofed. In particular, the router that is connecting the hosts is responsible for guarantees that my hosts are not sending spoofed packets. So you could be using mobile IP at the destination, or you could be using static IP. It is completely independent. Does that make sense? So this approach is good if everyone in the internet, by everyone I mean routers, if every router in the internet knew who it was connected to and ensured that in the packets they generate, they are putting in the IP addresses that they should be putting in. There is no IP spoofing problem in the internet, and that is an ideal solution, right? However, given that you cannot impose, practically you cannot impose anything in the internet, which means some people are going to deploy it, some people are not going to deploy it. If a network deploys ingress filtering and another network does not deploy it, the network that doesn't deploy can still spoof the network that is deploying it, because no one controls what you put in what network Y, who's not deploying, puts in its packets. And if network X is deploying it, it could still get spoofed, as in someone else can spoof its address range. Is that clear? So here, of course, the router denies it because it knows who can come. So the main shortcoming of this approach is that in the case of partial deployment, you cannot, in the case of partial deployment, those who are deploying get nothing to deploy it. They have no incentive for deploying this thing. So what could we do to provide them with some incentive to deploy? And that's essentially what our approach tries to do. So every router, every deploying router would perform ingress filtering, which means it takes responsibility for the correctness of the source addresses that go in the packet that it routes, right? And it puts a simple pattern, like a bit pattern. You can think of it as a 64-bit pattern or 32 bits, etc., to indicate that this packet has the correct source IP address. The next deploying router, every other router in the internet just does routing the way it would do today. If they weren't deploying it, they would not be concerned with the extra marking that's